Welcome back to the workshop. We want to continue taking a look at section 2.1, set operations. And in fact, we'll actually look at set operations in this video. All right, so set operations are manipulations or combinations of sets as a very general description here. So let's look at the different ways that we can do that. So the union of two sets A and B is denoted A union B. And the union is the set which contains all elements from A and B. So we can express A union B in set builder notation, and it would be, of course, curly brackets. It would be all of the elements X such that X belongs to A or X belongs to B. And we immediately have the correction for the last thing that we looked at in our previous example. B being or containing the elements 2, 3, 4 is equal to the union of sets C and D. Right? Because the union would contain the same things that are in C and or C or D, right? So it contains 2, 3, and 4 because 2 is in C, 3 and 4 are in D. So all of those are in the union. Awesome, easy enough. All right, we also have the intersection of two sets A and B, which is denoted A intersect B. And we can express that as, or in set builder notation, as A intersect B is equal to. Here, the intersection is the elements that belong to both, not one or the other, but both. It has to belong to A and B. So it's the elements X such that X belongs to A and X belongs to B. So if I were to return back to this example and say, well, what's the intersection of sets C and D? Well, they have nothing in common. There is no element that belongs to both C and D. 2 does not belong to D. 3 does not belong to C. 4 does not belong to C. So there's nothing in common. Their intersection is empty. Let's see here, make sure we complete the notation for set builder notation there. All right, so let's take a look at a really quick example of finding the union and intersection of these two sets. So you might notice that this is the collection of even numbers or multiples of 2, greater than 0, less than 20, and then these are the multiples of 3, greater than 0, less than 20. So A union B would be any number that is divisible by or is a multiple of 2 or 3. So that would be 2, 3, 4, 6, 8, 9, 10, 12, 14, 15, 16, and 18. Okay. 2 belongs in A, 3 belongs in B, 4 belongs in A, 6 belongs in A and B, 8 belongs in A, 9 belongs in B, 10 belongs in A, 12 belongs in A and B, 14 belongs in A, 15 belongs in B, 16 belongs in A, 18 belongs in A and B. So that's where they come from, right? It includes things from A, it includes things from B, it includes things that belong to both. Now, what about the intersection? A intersect B is simply the elements that are in common to both. So a multiple of 2 and 3, or simply a multiple of 6. So 6, 12, 18, 6, 12, 18 are the elements that are in common. Excellent. So our next definition that we want to take a quick look at is we can say that two sets are disjoint if their intersection is empty. And that's exactly what we looked at in our previous or in our example from the first video, set C and D were disjoint. C had just 2 and D had 3, 4. But let's take a look at a different example here. Let's say that A is equal to 1, 3, 5, and 7. And to make things really simple, let's make B be 2, 4, 6, 8. Of course, they have no elements in common, so they are disjoint. A intersect B is the empty set, and we can say that A and B are disjoint. Excellent. All right. So sometimes it would be nice to refer to elements that are in one set but are not in another set. And that brings us to our next definition of the difference. So the difference of two sets A and B, denoted by A minus B, is the set of elements that do belong to A that are not in B. So we would express that as A minus B, which would be a set minus B, is equal to, we can write this in set builder notation. So it's the elements that do belong to A and do not belong to B. So we could write it that way. All right. So if we consider the same sets that we looked at back here, let's find A minus B and B minus A. So the only thing that we can take away from a set is the things that they have in common. So if I have A minus B, I would include 2 and 4 because 2 and 4 are not in B. They are in A, they're not in B. 6 I would not have because 6 is also in B. I would include 8 and 10 because they're not in B. I would not include 12 because it is in B. I would include 14 and 16 because they are not in B, and I would remove 18 because it is in B. So A minus B are, or is, right, this is the set which contains the evens or the multiples of 2, which are not divisible by 3, or not a multiple of 3. So we have 2, let's write that a little more clearly, 2, 4, 6 is a multiple of 3, so I do not include it. 8, 10, 12 is a multiple of 3, so I do not include it. Yes, 12 is not a multiple of 3. So 14, 16, and then 18 is a multiple of 3, so I do not include it. Now the other way, I'm going to take the set B and I'm going to remove all the multiples of 2. So I have 3, and then the next number would be 6, but it's a multiple of 2, so I remove it. So 3, 6, 9, 12 is a multiple of 2, so I do not include it here. 15, and then 18 is a multiple of 2, so I do not include it. And that's it for B minus A. Excellent. So one more, or a couple more definitions for us to look at, and then we'll call it all set for this video. So a set containing all the elements of interest in a particular situation is called a universal set. If you're working in statistics, that's typically referred to as your sample space. Just a side note here. But universal sets are typically denoted by U, so we'll use that. All right, now we get another set operation with this new definition of universal set. So given a universal set and a subset of that universal set, so A is a subset of U, the set U minus A, so we're not really looking at a new definition, I guess, but a new idea, a new situation. So when we have a universal set, this difference is actually called a complement. So it is the complement of A in the universal set U, and it's denoted by A bar. Okay, so if you see A bar, that means that we're working within a universal set. All right, there are some texts that also denote this as a raised to the c or a prime. Both of those are used as notation for the complement. All right. So if we, again, use the sets A and B as we used previously, the multiples of 2 and the multiples of 3 between 0 and 20, not including, let's let the universal set be all of the natural numbers between 0 and 20. Here we're using the definition that the natural numbers do include 0. Some books do not include 0 in the natural numbers. All right, so we're including 0 here. So we want to determine the complement of A and the complement of B. So A complement, if A is the set of numbers greater than 0 but less than 20 that are multiples of 2, then its complement would simply be the things that are not multiples of 2 and include 0 and 20. Okay, so we have 0, 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, and 20. So that's all the numbers between or from 0 to 20 that are not in A. What about B? Well, B again is the numbers between 0 and 20, not including 0 or 20, that are multiples of 3. So if we look at the complement, we're looking at the things that are not multiples of 3, and then including 0 and 20. 0, of course, is not a multiple of 3 anyway. But 0, 1, 2, 4, 5, right? So I removed 3 because it is in B. I removed 6 because it is in B. All right, 6, 7, 8. Remove 9 because it's in B. 10, 11. Remove 12 because it's in B. 13, 14. Remove 15 because it is in B. 16, 17. Remove 18 because it is in B. 19, and 20. There we go. Simple as that. So there's a couple different ways that you can look at complements, of course, by definition, but we also give kind of a description of the numbers that are in the set. A is the evens. So a complement would be the things that are not even. Of course, we include 0 and 20 because 0 and 20 are not in A. All right, so I think that's pretty good. And we'll pick up on this theorem in our next video. So set operations, we're all set there. We'll move on in our next video.